one-dimensional quantum mechanics. I will quickly just go through various aspects like wave functions, expectation values, operators, etc. And we'll start doing problems pretty soon, like in just a brief review, and then immediately we'll start doing problems. Through problems, we will discuss as and when it's necessary. Okay, so let us start. So if you have a system, any system, so what is this system? A quantum system we have in mind. Our examples are particle in infinite square well. If you have an infinite square well, there is a particle in a potential, basically in a potential. So these potential can vary. One of them that we know of is infinite square well, harmonic oscillator, hydrogen atom. Hydrogen atom is also a particle in a potential. In hydrogen atom, the electron is revolving around a nucleus. Actually, it's like a central field, central potential, where there is an attractive force coming from the positively charged nucleus and the electron is revolving. These are the systems that we talk about. So these systems in quantum mechanics are described. These systems are described by something called wave function. Psi of t, this is what is called wave function. So this tells you, described as psi of t, this tells you state of the system. You know very well that this has to be normalized, etc., etc. And the time evolution of this state is given by Schrodinger equation. Schrodinger equation is very straightforward. You have something like this. This is a solution to Schrodinger equation plus V. But when potential is independent, when potential is independent of time, if you have a potential which is independent of time, it changes. How? Your psi of xt can be written as some function, let's say psi of x, a space function which depends only on x, and a time function which depends only on energy and time, something like this. And you know that from here, this psi of x, what is this psi of x? This satisfies Schrodinger equation, but we call this Schrodinger equation time independent Schrodinger equation. Let me write it once and for all. The x squared plus v psi is equal to E psi. Here you have E. What E is? E is energy, etc. Now, let me just say this is called stationary states. We are going to look at these kind of problems where your potential is independent of time mostly. And then there you have to solve only for psi of x, and then you will go on. This is a pretty basic thing. If you looking at the general solution of Schrodinger equation, if you have a general solution, how do you write a general solution? General solution of a Schrodinger equation is written as, you will have many bound states which are given by psi n of x. Here n goes from 1, 2, and so on. And each one has a factor En of t. And there is a linear combination which goes as n is equal to some 1 to infinity or 0 to infinity. There will be many states. This is called general state. Mostly we don't know where the system is. So when you don't know where the system is, when you make a measurement, let us say You make a measurement. Make a measurement. What kind of measurement? For energy. You make a measurement for energy. You have to be specific. So if you're making a measurement for energy, you're measuring energy, then you can say the probability to get, let us say E2 is given by, what do we the probability? Maybe we'll just say psi 2, and then the big function, you take modulus and whole square. This is a probability to get energy E2. This is how you calculate probabilities. So this is the general theory. You also need to remember a few things. For example, infinite square well. Infinite square well. Infinite square well, how does it look like? Infinite square well, you have x-axis here, and the potential goes to infinity, and you will say that V of x is 0 when 0 to a, when x is between 0 to a, and otherwise infinity. You will have this kind of a description. If you have particle in this infinite square well, there are wave functions given by 2 over a sine n pi x over a, and energies, eigenvalues of energies, which are given by, how do I write this? H square over 2m, that is a momentum square. There's a k square. K square values are quantized, and they have something like this. So this you must remember. Another system that we all very often talk about is harmonic oscillator. Harmonic oscillator. Which harmonic oscillator is? It's a particle moving in a potential which is half m omega square x square. So if we are looking at Hamiltonian operator is p square over 2m plus half m omega square x square. You can write this in terms of Dagger operators. Rising operator. A Dagger is something. Let me define what A Dagger is. A Dagger is 1 over 2m h cross omega square and m omega position operator minus I momentum operator, and then there is the A. A is written as same thing, 2m h cross omega m omega x prime plus I p cap, and then your h cross, your Hamiltonian becomes h cross omega A dagger A plus half. You can go to a basis where A and A dagger will have some eigenvalues, and you can solve this harmonic oscillator system. You probably know. So these are the things that we have in mind. Can anyone tell me what is the ground state of harmonic oscillator? Ground state of harmonic oscillator. Roughly, how does it go?
1 by.
So no, yeah, the form itself.
E to the power Gaussian function. E to the power.
Yeah. So you know that it's something like this. Right?
Yes, sir.
Yes. If you have at x is equal to 0, if you have this kind of a function at x is equal to 0, there is a minimum. Then you have this kind of a wave function. What about first excited state?
Multiplied by x.
Yeah, very good. So there is a x minus ax square. Up to constants, there are constants too. you need to remember the general forms, at least ground state and first excited state. So this is, I think you need more information, but at this much, everyone should have in your mind. This is essential, and this one you don't derive, you commit to your memory. There are many things, at least this much which is needed. You need to commit to your memory, and you go through it the multiple times. At this level, you need to like bring it whenever you need this information. You should be able to bring it back. Let us see some problems now. So I have one here. This is pretty easy. Let us read it. The wave function of a particle is given by. So wave function is given. Whatever it is, wave function is given. So you can see this is a time independent system. The particle is moving in a potential which is time independent. So you can actually write time part separately, space part separately. Here the space part is given, and it's a linear combination of phi 0 and phi 1. These phi 0, phi 1 are normalized eigenfunctions of energy operator or Hamiltonian operator. So phi 0 is an eigenfunction with eigenvalue E0. Phi 1 is an eigenfunction with energy value E1. So they are basically ground state and excited state. So someone says find expectation value in this state. How do you find expectation value? Energy expectation value in this state. You all know this, but we need to do this in the first 2-3 problems so that we get used to what we are going to do. So by the time the next session comes, we'll be like thorough with the basics. So one of the things is finding expectation values. You write it. These are wave functions. Expectation value, how do I write? This is a one-dimensional problem. I integrate our entire one-dimensional line, and maybe I'll write psi star, and then I'll put energy operator, which is Hamiltonian, and then write psi again and dx. This is what expectation value means. But what is h psi? H psi can be written as, let us put in some values. Psi star is 1 over root 2 phi 0 star plus phi 1 star. Okay, let me ask a question. Is this correct? Is this correct way to do it?
No,
Why?
we can use bracket notation.
No, is this the correct way to calculate expectation value?
The denominator should
Why
be normal.
denominator? Why what denominator?
The integration of probability density size mod square.
So most of the time, this is correct when phi is normalized. Psi is
Normalized.
normalized. If psi is not normalized, what you have to do is you also have to divide this with psi stays psi dx. Okay. So this is how you calculate. Let's do it. Let's do psi stays psi here. Psi star psi integral dx. What is psi star psi integral dx? Should be some value. Can anyone tell me what is the value of psi star psi integral dx? 1. Given this, I want you to do psi star psi dx.
3/2.
Someone said 3/2. Let's see how. So when I do psi star psi, I get 4 terms. Why? 1 over root 2 phi 0 star phi 1. This is psi star, and I do again phi. I put in phi. This is dx. When I multiply, I get 4 terms, right? If you look at 4 terms, so what is the 4 terms you get? 1/2, 50 star, 50. This is one term plus 50 star, 51 dx. And there is a 1/√2 plus integral 1/√2, 51 star, 50 dx plus integral 51 star, 51 dx. If you see these 4 terms, this is non-zero, this is non-zero, but this is 0. This is 0. Why? Because these are normalized eigenfunctions which are orthonormal. So since they are orthonormal, these cross terms are 0, and then 0 star, this one gives you half because they are normalized. This one gives you 1, that gives you 3/2. So that's how you do it. Similarly, we can figure out the numerator. Numerator is how much is numerator? Let us see now. If I'm interested in psi star, h psi r, integral psi star is something 1/√2, pi 0, pi 1 with stars. The Hamiltonian is acting on the second part, which is phi 0 plus phi 1, and you integrate. This one is what? This is numerator. You can quickly say, again, when Hamiltonian is acting, you will have first part is same. Hamiltonian acts on the second function, gives you energies. One is E0. E0 is the one. E0 over √2 pi 0 plus when Hamiltonian acts on the second one, because they're eigenvalues of this Hamiltonian, you get something like this, and then dx. You can multiply again. Again, there are cross terms. Cross terms will go to 0. Only the normalized ones will come to give rise to this, and then you will have something like this. So expectation value in this state, the numerator is E0/2 plus E1. Denominator is 3/2. The total one you should have E0 plus 2E1/3. I think, yeah, this is how you do it. Okay, how many of you know how to do this problem? Let us see. Can you raise your hands? 1. Only 1 person. Okay, there are some. How many of you think I'm going too fast? Please keep your hands down. Okay, no one. That's good. Okay, let's look at second one. Next problem. So here there is a similar problem. The wave function of a particle at a time t is equal to 0 is given by this. Again, the wave function is given at time t is equal to 0, which is a linear combination of two normalized eigenstates of energy. These two are normalized eigenstates of energy. U1 has eigenvalue E1, U2 has eigenvalue E2. Now, this is a state at t is equal to 0. This state evolves. After a time t, what happens? Because these are stationary states. Evolution always happens like this. This one plus the state U2 evolve with energy E2. That is the meaning of stationary states. Since we are talking about time independent systems where the potential is independent of time, once we know eigenvalues of energies, they evolve in this way. Now, question is, he's asking at what shortest time, after a time you have this, asking at what shortest time psi of t becomes orthogonal to psi of 0. That means orthogonal means the inner product between psi of t and psi of 0 is 0. When does that happen? You have to figure out that time. So you start with this condition and then write it. So psi of t, let's consider psi of t on this side, psi of 0 on this side, and you just write whatever we have. I think 1 over root 2, 1 over root 2 is common. Then there is a 1 over 2 here, and you have u1 here, u1 is have some value minus, this time it's plus e1t over h cross. There are two states. Let me do it through two states. So they're testing how to do inner product. The first one is u1 plus u2. This one has here with 1 over root 2. And then I have here u1 with exponential plus I e1 t over h cross, plus you have u2 exponential I e2 t over h cross. This is one more conjugate of the first one. You take the sandwich these two. So again, when you do this, there are four terms. U1 can be sandwiched with U1, U1 can be sandwiched with U2. Similarly, there are four terms. U1, U1, U2, U2, and cross terms. Cross terms go to 0 for the same reason. But the surviving terms, 1 over root 2, 1 over root 2 is 2, 1 over 2. Let me write it. The surviving terms are U1, U1 with I e1t over h cross plus u2, U2 cross product I e2 t over h cross, and this gives you half. And here you have I e1 t over h cross plus I e2 over t over h cross, and you do this. So this should be 0. You have to solve this problem. You equate it to 0. This should be 0. Solve it for t. You solve it for t. You can try. All you have to do is multiply and do some manipulation. Let me do it. 2 you multiply, 2 will go away. And then you multiply both sides with exponential minus I e1 t2. So if I do that, this is nothing but 1 exponential I e2 minus e1 t over h cross is equal to 0. So from here you can figure out when can this exponential factor is equal to minus 1. That is minus 1 equal to exponential I e2 minus e1 t over h cross. This happens only when this phase factor is pi. When phase factor is pi, this becomes cos pi is -1, sin pi is 0. So this implies E2 minus E1 over H cross times t must be pi. So from here you can say that time at which these two wave functions becomes orthogonal is this. Okay. So that's about this kind of. So in both the problems, if you noticed, the idea is you're able to do manipulations based on wave functions, whether it's inner product or expectation value. They have similar techniques. I have one more problem where you have to calculate uh, expectation value and say that this is a minimum. So this problem is a little more tricky. This is a harmonic oscillator. So let us try to figure out few facts about harmonic oscillator. First thing is, let's read. Consider a normalized state. It's a normalized state. State is normalized. You don't have to do anything. And it is a 1D harmonic oscillator. And it has 0 and 1. So 0 is the ground state. 1 is the first excited state of harmonic oscillator. So the system is in the linear combination of those two states. Here B1, B2 are real constants. And if that is so, first you need to figure out expectation value of the position. Expectation value of the position operator. And question is, when does this expectation value, which is calculated, becomes minimum? So that's the sort of thing. So what is expected of you is if you have this is 0. Does anyone know why this becomes 0? Expectation value of x in the ground state is 0.
Mean position.
In harmonic oscillator, expectation value of the position operator in the ground state is 0. Okay, if not anything, at least you should know these two facts. First, let me show that this is 0. This you must know. Let's spend some time on it. How do we prove this? There are multiple ways of proving it. Okay, one way of proving, I will start writing integral representation for this. Ground state means integral representation. How do you write this? This is what it is. And this integral is a symmetric integral, goes from -infinity to infinity. Now, we all know roughly the form of ground state. Harmonic oscillator ground state is, someone said it's Gaussian, right? If it is a Gaussian, you can see this is an odd function. Odd function with symmetric limits. Size 0, both are odd function, even functions. X is odd. So totally it's an odd function. With symmetric limits, it goes to 0. Similarly, you can show that 1, if you have a first excited state, expectation value in the first excited state, how do you do this? This is x minus x square. Roughly, this is the first excited state, apart from the constants. X minus x square. This is first excited state. So you integrate it. Again, you see the whole function is -infinity to infinity, an odd function. Odd function with symmetric limits goes to 0. That I hope I don't have. This is one way of looking at it. So let's see one more way of doing the same. Maybe you probably remember somewhere we have written that a dagger is something. What is a dagger? M omega x prime minus IP. It's some, I think, 2m h cross omega with square root. Similarly, a we have written as m omega x cross plus I p hat this. From here, you can invert this and write what x is. X operator. X operator, if you invert, you just add both of them and you get x operator. What is this? If you add, all you have to do is add. If you add, you get x. P's will cancel. And then there is a factor. I have to figure out this factor. You please do it. You will see that this factor is, you remember only one, and then you can figure out the rest. Something like this. There is a factor, and x is a plus a dagger. Now, if you are interested in looking at this, you can use this. So this says some constant. Constant is whatever it is, h cross 2m omega. I'll write it for clarity. A dagger plus a 0. Does anyone know what this is? So let's look at here. When A acts on the ground state, it gives you 0. When A dagger acts on the ground state, it gives you 1. It's that. So you can use those things and figure out. And you know that these are all normalized. If you have an inner product between 0 and 1, it's 0. If you use all these three results, you will figure out that this is 0. Similarly, you do this. Then you can do same again. You please try and do it. But this is another way of seeing the same fact. Expectation value of x operator in the ground state and first excited state is 0. This is a property of harmonic oscillator. This you must know. So now you have seen it in two ways. One is in integral representation. Other one, this is called algebraic representation. This is doing this side of a thing is algebraic representation. Let's get back to our problem. What is our problem? In our problem, psi is given and you have to calculate x. With these facts, we can go further. We can compute this in the state psi. And so apart from maybe there is something, there are 4 terms again. The 4 terms are, what are the 4 terms? You will have b1 square because these are real. These b1, b2 are real. I can say this is this much plus b2 square this much plus there is a b1, b2 0 and 1 plus b1, b2 0 and 1 and 2. 1 and 0. Okay. X is Hermitian operator. So if you have a constant C times 1 x 0, this is equal to, because x is Hermitian operator, this is equal to C star. You can do this. And this is equal to C star 0. X is Hermitian, therefore this is this and this. So if you have inner product something like this, you can convert them back. So since B1, B2 are real constant, C is usually complex, but here B1, B2 are real constants. I can write this as B1 square 0 x0 plus B2 square 1 x1 plus 2B1 B2. Maybe I'll just put this. Well, we have seen this goes to 0. This goes to 0 and only this part. This is 2B1 B2 0 x1. If you want, you can compute this using the algebraic method or any method, but we don't need to, because what we are interested in finding expectation value of x in this state. Condition for this expectation value to be minimum. We have to figure out when this becomes minimum. So when does this becomes minimum? This is normalized state because that B12 square is equal to B2 square 1. And then 2B1 B2 is equal to, we can write it as B1 square plus B2 square minus B1 minus B2 whole square. You can do that. So if you do that, this is B1 square plus B2 square minus B1 minus B2 whole square, then 0 x1. This becomes minimum when this is 0. This is minimum. This is 1. B1 square plus B2 square is 1 minus B1 minus B2 whole square. You can rewrite this. Okay, this one is rewritten like this. Now you can clearly see this coefficient 1 minus so and so becomes minimum when B1 is equal to B2. Then only it becomes minimum. When B1 is equal to B2, this is minimum, and that gives you some values. B1 probably B1 is equal to B2 is equal to 1 over root 2 because they are normalized to 1. So that's how you can figure out this. This is another sort of thing. You can see this is pretty long. So they'll expect you to remember quite a bit. Also, even though you know how to calculate this, here there is a trick. You can see this 2B1 B2, the product of B1 B2 with B1 square plus B2 square is equal to 1. When is this becomes when does this become minimum? That's the question you have to figure out. For what values of B1 and B2 this becomes minimum? Okay, that is saying that this is like an ellipse, right? If we have B1 square plus B2 square is equal to 1 means this is an ellipse. If B1 and B2 are not equal, and the area, you can say the area is minimum when B1 is equal to B2. It becomes a circle. That's one way of looking at it. Let's look at this one.
Excuse me, sir.
Yes.
Sir, you are going little fast.
So do you understand the last problem?
Sir, there are certain things I did not understand.
Okay. But did you understand how to compute this?
Sir, why isn't B star B1 in place of B1 square?
Why isn't?
B1 star B1.
Okay. In the problem, it's written that B1, B2 are real constants.
Okay.
Okay,
Sir,
that's why. Otherwise, you're right. There has to be complex numbers.
Sir, how does B1 square plus B2 square become 1?
Because it's written that in the problem, psi is normalized. Let me go back. Here, it's a normalized state. That means B1 square plus B2 square has to be 1. That you understand? Psi normalized means b1 square plus b2 square is equal to 1. Should I show it?
Okay, sir. Understand, sir. Understand.
Okay, that's good. You are. Please ask questions if you have any. There is no point in going too fast, covering too many problems. And if you don't understand, you please ask. Do you have any other questions? I'll wait here half a minute or so. And if you have any questions, please ask. See, in all these problems, yeah, well, let me just say one thing. In all these problems,
Okay.
knowing concepts like expectation value or doing something, that's only one step. In every problem, either you have to do some integration or you have to do some analytical manipulation. So you also has to be thorough in integrations or few trigonometric techniques. So otherwise you will not be able to compute the final answer. Okay, please ask. Someone was about to ask me something.
Sir, why ground state and first excited state have zero position operator equals 0?
This one, right?
Yes. Yes, sir. Yes, sir.
So do you know that this can be written as this?
Yes.
Okay. Now you know this. Do you agree that this whole thing is an odd function?
Yes, sir.
So odd function under minus infinity to infinity is
Sir, I'm asking what about the second excited state?
second excited state also. If you look at algebraically, this is what happening. You can see second also. If you what is this function again? Odd function, right?
Yes, sir.
Okay. Now you maybe let me just do it one more way. If you have simple harmonic oscillator, ground state look like something like this, symmetric with respect to 0. This is a ground state, right? If you look at the momentum has both positive and negative. The average value of x is 0 because half of them will have momentum. Half of them will have momentum in this direction. Half of them will be moving in this direction. That is why average value is 0. It's symmetric with respect to x. If you look at the first excited state, looks like this. Sorry, I'm trying to make it symmetric. First excited state it's symmetric, but it goes like this. This is also with respect to this. There is a symmetry on either side, and there is a momentum on this side and momentum on this side. They are in opposite directions. That's another way of looking at it. If you understand this. Anyway, let us read this problem. This is very straightforward. Everyone understand what this problem is? Can you please read? Take a half a minute and read. And I want to see how many of you can do this. So there is a particle in infinite square well potential, and it is in the ground state. And then you need to find a probability to find the particle in the interval between -a/2 and a/2. But you all know about infinite square well. If you have infinite square well, -a/2 and a/2. What is the ground state? Can anyone tell me what is the ground state?
root 2 by
√2 by a.
Okay. √2 over a.
Sin n pi x.
Cos n
Huh?
pi x by
Cos. Yes, a cos for symmetry grounds.
But it is between -a to a. -a to a. So
Cos.
now
2a.
now what to
root
do?
√2 by 2, root of 1 by a
2 over length.
2a.
Actually, length 2 over length. Length is 2a here. Total length of the well is width of the well is 2a. 2 over length is 2a. It has to be sine or cos.
cos
Is it sine or cos?
cos
Round. Someone said cos. It has to be cos. It's not sine because it's a symmetric well. Only when it is cos, it goes to 0. It has to go to 0 at end point. If it were a sine, it will not go to 0 at end point. Let's see. If it cos, we are interested in ground state, pi x over length. Length is again 2a. You can check. You substitute x is equal to -a and a, it goes to 0. So you will get a wave function which looks like this. So this is the ground state. So this is the difficult part. Figuring out they didn't give you a regular infinite square well. If you remember regular infinite square well, you will not be able to write this. So this is different. So first obstacle is writing the wave function. Once you write the wave function, you know you are interested in probability of finding a particle between a/2 and a/2 and -a/2. That means all you have to do is integrate between -a/2 to a/2 psi 0 star x psi 0 x dx. This is a like long calculation, but at the end you should be able to do. And you want me to do, I'll do it. You get something like this. You have to do it. So there will be a cos square. When you have a cos square, you write that into cos 2 theta. If you have a cos square theta, you will write in terms of cos 2 theta and 1. And then you do the integration. And yeah, something like that. So please try this. And please remember, how did we notice that in general, if you have this 2 over length, remember, if you have cos or sine, depending on whether it's symmetric or thing, n pi x over length, we have something like this. This is a general structure. And energy also. Energy also changes for this system. What is energy? Energy is h square over 2m, n square, pi square over length square, width square. Width is 2a. So this also changes. So there can be tricky questions like that. Let's try the next one. This is another thing. This is also, can you please read it? What is the difficulty in doing this? This looks like a straightforward problem. What is the difficulty in doing this? Can you please read and understand and figure out what is the tricky part in it?
Hello.
Yes. Yes. So how do we find its psi? Its psi is given as psi h psi over, if psi is not normalized, you do this. This is the expectation value of this. But how do you do it? How does h acts on psi? What is the meaning? How does Hamiltonian operator, energy operator, acts on psi? How does it act on psi? What do we get? Psi is given as sine cube. Does anyone know how? In a particle in a box, what do you know? So this is this kind of a particle in a box. Here it is 0 and a, and we have psi n of x is 2 over a, and this is sine n pi x over a. If you have this kind of a stuff, if you know that Hamiltonian acts on these wave functions and gives you En. But what you're given is something very different. You're given a completely different wave function, which is a. What is given? A sine cube pi x over a. Now, if you want to figure out expectation value of the energy operator, you need to know how h acts on psi. How do we figure that out?
We write the sine cube in terms of psi.
So you always look for whether we can expand this general state psi in terms of eigenfunctions of energy operators like this. These are eigenfunctions. Eigen states are functions of energy. Can we write this in terms of eigenfunctions of energy? Can we write this? Can we write sine cube into some signs?
Yes.
What is this? Sine cube of x is how much?
3 by 4 sine 3x.
3 sine x. Does anyone know?
minus sine 3x by 4.
Something like this. Sine cube x. Sorry. So I'm trying to do what I'm trying to do is this. Sine 3x is equal to 3 sine x minus 4 sine cube x. You can use this. But how many of you remember this? If you don't remember, do you know how to figure out this relation? How to figure out this relation? Suppose you forgot. You forgot sines are 3, 4. How do you figure out? So what you can
Sine
do?
2x plus x.
Sorry? Sine
2x plus x.
sine 2x plus x. Okay. And then you write sine a plus b. And then you do a lot of manipulations. So you should know how to figure out these things also. Yeah, like she said. What is your name?
Sir, Huda.
Huh?
Huda, sir.
Got Huda. Oh, Huda. Okay. So what you can do is you can write in terms of exponentials also. The sine 3x is imaginary part of this. You can write this as e power ix whole cube and write this as cos x plus I sin x whole cube. And then you can write some sort of cubic equation. And you are interested only imaginary part, not everything. So you can write imaginary part, imaginary part. Imaginary part of this expression, you don't need cos cube x, sin cube x. If you can try and do it, and you will see that imaginary part of this expression is minus sin cube x plus 3 cos square x times sin x. This is the imaginary part of this. That's very easy. And then you can write cos square into whatever that you want, minus sin cube x plus 3 1 minus sin square x times sin x. That's it. This gives you your formula. You can do that. So now that we know, you can reverse this and write as so you can write this as 3a over 4 sine pi x over a minus a over 4 sine 3 pi x over a. So it's basically, what is this? Three a over 4. You need to have a root of 2a. Then let me write a over root 2. And then this becomes the first function, first eigenvalue, psi 1 minus a over 4 root of a over 2. And then this becomes third one. Oh, third eigenvalue. So you can do that. Can you figure out a normalize? If you normalize a, how do we find a after normalizing? So normalize psi. Normalize psi and find a. What is the normal after normalizing? Can you find a? You can do that. That's not difficult because psi 1, psi 3 are orthonormal. When you take the inner product between psi 1 and psi 3, it's 0. Between psi 1 and psi 2, it is 1. So what you get is 9 a square a 32 plus a square a 32 is equal to 1. From there, you get a is equal to 32 over 10 a. This is a square. So from here, you can figure out what this is. Now, let's come back to our problem. So now we know that what this is. Where are we? We can figure out expectation value. Expectation value of h psi. Expectation value. We'll write it like this. So a square over 16 a over 2. That is the first part. a square over 16 or a over 2, and then expectation value of this. Should I write it as, maybe I'll write it integral here. 3 psi 1. 3 psi 1 star minus psi 3 star, and you have Hamiltonian 3 psi 1 minus psi 3 and dx. So a square over 16, a over 2. So only things that survive are 3 3s are 9. After all that is, let me write one more step. Then it will be good. One more step, I'll write it 3 psi 1 star minus psi 3 star. When it acts on each one, you get 3e1 psi 1 minus e3 psi 3 dx. Now it's straightforward. A square a over 32. When you do this, you get 3 times 3, 9e1 plus e3. This is what you get. But e1 and e3, what is e1? e1, 9e1 is 9 times pi square h square over 2m a square. But e3 is again 9 times pi square h square over 2m a square. So a square over a 32. When you add both are same, you get 9 times pi square h square over 2m square. 2 will cancel, both are same, twice m a square. And then you can figure out what a square is. A square we have already written somewhere. 32 10a and whole. 32 10a, that is a square. A over 32 9 pi square h square over m a square. So that gives you, I think, 32 will cancel, 32 will cancel, a will cancel, a goes away. 9 over 10 pi square h square m a square. So this is pretty long, but end result is this. Usually this is what is expected of you. You are able to get to this end. Everyone understand this problem how to do? So it starts pretty straightforward. There are various aspects in this. Let's look at it once again. It has infinite square well. We know what to do with infinite square well. But trick is, there is a very complicated trigonometric function, and they are expecting you to write this trigonometric function in terms of signs, eigenstates of energy. Once you write psi in terms of eigenstates of energy, here we have written. Where did we write? Did we write anywhere?
So can you show me that normalized
Here.
part? Yeah.
Here. So here we have written psi in terms of normalized.
Okay, sir.
So see, one more thing. How many of you can read normalization just by looking at this? After this, you should be able to see this. How many of you can see it? Because psi 1 star psi 1 is 1, psi 3 star psi 3 is 1, psi 1 star psi 3 is 0. Cross terms are 0. only ones that contribute are psi1 star psi1. So the square of this plus square of this should be equal to 1. So if you do enough number of times normalization, you don't have to go through these steps. You should see it at this stage. If you attend quantum mechanics lecture for 40 classes, and you should be able to do this very fast. That's the idea. So here also, when you look at this, you shouldn't go through all these steps. I'm doing it for once, but usually when I do it, I already know here there is a, but I have to make sure I'm not gonna make any mistake. So I'll be careful. I still write it, but I sort of know that this acts on this, gives me some energy. This acts on this energy, and then but cross terms goes away. So I know what terms comes out. So that you should have in mind. You shouldn't go through all these, and you should have that overall idea. Okay, any questions? If you have any questions, please ask.
Sir, can you go to the previous slide once?
This one?
Sir, yes, sir. Sir, in this equation, xi x equals a sine cube pi x upon a. In the third step,
Here.
when you
Here.
write sine pi x equals a
This
by
one?
2 root a
This
by
one?
2.
This one.
Yes, sir. Yes.
Because each one has a root 2 over a, right? What is psi1? What is psi1? Psi1 is 2 over a sine pi x over a, right?
Yes, sir.
So but this term, this root 2 over a is not there. I have to multiply and divide.
Okay, sir.
Yeah, that's very tricky, right?
Sir, a little bit only.
Yeah, no, but this is the point. See, after writing this, you will forget about normalization. Actually, if you don't do this, you will not get correct answer. After writing this step, if you think that you're done, this is the first one, this is the third one, yeah, I'm done. That's wrong. You also have to make sure they are correct up to normalization. Okay. Now, this is also similar vein. We are doing today a lot of inner products, expectation values, but it's good. You should be like thorough with this. I don't know. I think I shouldn't do this because after doing all this, I'll expect you to do this part easily. You first read this and understand. Let me give you an answer. You will also find it at many places. Answer is 5 is pi over 3. See, I have given you a Hermitian operator, normalized eigenstates, eigenvalues 1 and 2 numbers. And you're given two states, some combination of these. And you're given this expectation value of 7, 4, and this. Use this and figure out phi and theta. So please, you do it. This is not difficult, but I want you to do it. After doing all this, you should be able to do it. And if you are not able to figure out, and you ask me, maybe tomorrow. This also. The eigenstates corresponding to eigenvalues E1 and E2 of a time-independent Hamiltonian are given. If at t is equal to 0, the system is in the state so and so. Find this. This is very easy. I want you to do it. This also you should do. Okay, this I want to discuss. Do we have time? Yeah. This is I think the last one I'm gonna do today, but this is interesting. The energy eigenvalues of particle in a potential Vx. If you are given a potential Vx is equal to half m omega square x square, you say that it has eigenvalues n plus half h cross omega, right? If you have a potential Vx is equal to half m omega square x square plus a constant, what are the eigenvalues? Can anyone tell me? Energy? It is the constant will get added. Nothing but it's that. Now, this problem can be written as something like this. Can anyone see how this potential Vx, this potential, can be written as harmonic oscillator potential plus a constant? We are given a potential Vx is equal to half m omega square x square minus ax. So I can write this as half m omega square x square minus half I have taken. So 2 a over m omega x. I can complete the squares and write x square minus 2 a m omega x a square m square omega square minus a square m square omega square, add and subtract, completing squares, half m omega square. This is x minus a m omega whole square minus a square over m square omega square half m omega square. So this is half m omega square. You can think of this as y square minus m omega square. This is what? A square m 2m. If I have done it correctly, I think I have done it correctly. There is a
2a by
square.
m omega.
There is a square. This is 4. This is 4. This is 4. There is a square. So this is a square. M will cancel. 2 omega m omega square. Yeah. This is what it is. So you can see this looks like harmonic oscillator. If you have del x, it becomes, if you write x, if x goes to, let us say, y, like if x goes to something like y is equal to x minus a m omega square, then del x will go to del y. So it's a constant shift. So in the differential equation of Schrodinger equation, this kinetic part will not change. Only the potential part changes. With this new potential, your Schrodinger equation becomes minus h square over 2m del square y square. The potential becomes half m omega square y square. This minus a square over 2m omega square will be added as a constant. You have to solve this. If you solve this, you will find that energies En are nothing but shifted by a constant, half n plus half h cross omega. That's a shift due to this constant. So that's the question. Okay, everyone understand this? Any questions on this part? Okay.
Sir,
Let's do.
after bringing into this form, directly we have to apply this formula, right? En equal to that one.
Yeah, you can directly write. See, this is for you to understand, I'm telling you. But once you know that this can be written as y square and some constant, you can directly write it. For that, you need to understand this part first. If you have this kind of a structure, a potential plus a constant, the eigenvalues will be shifted by a constant, nothing much. So it's based on that. They're trying to figure out whether you learn this fact or not. It's more like a fact based. Okay, here you have one more. This is also an interesting problem.
Hello.
Yes.
Yes,
Yes.
sir.
Yeah, please ask me. Hello?
Yes, sir. Sir, that is Ax minus A by M omega. So that is only origin shifting, no?
Yeah.
Okay, sir.
It's only origin shifting. But question is, when you have this kind of a constant shift, what happens to energies? That's the question.
Okay.
See, all of you have solved harmonic oscillator, right? See, have you all solved particle in a box? Let me just spend some time.
Yes, sir.
Contrast on these two. See, you all have learned particle in a box.
Yes, sir.
What is the potential at the lowest state? You will say Vx is equal to 0 and infinity, right?
Yes, sir.
Now ask this question. What if I made this like this? 0, A. My Vx is V0 and infinity otherwise. I can do this, right? The potential is not 0, but it's a constant. I shifted. This one is V0. This one is infinity. Here, this one is potential is 0 and infinity. I can do this. Now, what happens to energies? I'm giving you information. I'm not going to prove. So energies, what happens to energies? Nothing. Energies are independent of this shift. But it's not the same for harmonic oscillator. So please go back and check somewhere about these two things. So that's why that question has some relevance.
Sir, what happens in hydrogen atom problem?
If the energy is shifted by this, for both of them, energies are same. There is no difference. Energies are independent of V0. But in harmonic oscillator, energies depend on the bottom, the 0.0, the minimum. So that's the difference between particle in a box and harmonic oscillator. So I'm giving you information. I'm not proving you anything. Okay, let's look at this one. There's a particle of mass m in the potential. I'll stop it here. Maybe I will pick it up in the next class. It's better to stop. Let's talk